When a man on a frictionless surface, or frictionless rotating stool, extends his arms horizontally, his rotational kinetic energy does what? Does it increase, decrease, stay the same? It may increase or decrease depending on the initial angular velocity, may increase or decrease depending on his angular acceleration. I'm going to take a guess that it's not D or E. I'm going to take a guess that it's going to be one of these first three. It just doesn't make sense that the initial condition would happen. And depending on if it's increasing or depending on the angular acceleration, well, there's no forces that are acting on this thing. We're not actually having any torque on this. We're just changing our angular momentum. This is actually how we're going to solve this problem, is that we're going to know that the initial angular momentum is equal to the final angular momentum. And I'm going to assume that this person starts with I omega, moment of inertia and an omega. And it's going to go to I prime omega prime. And I know that there's one key fact that I prime is going to be larger than I. I extend my arms. When the man extends the arms, the moment of inertia increases. Which means if I rewrite this equation, this is I omega over I prime is equal to omega prime. This will actually tell me that omega prime is smaller than omega, by exactly the same ratio that I is larger than omega. And that's actually going to be a key point we're going to use later on. So let's figure out what the kinetic energies do. So my original kinetic energy is 1/2 I omega squared. My final kinetic energy, I'm going to designate it with a prime again, it's going to be 1/2 I prime omega prime squared. So now I'm going to start substituting in some values and see if I can get something that I can compare to K original. So what I'm going to do is I'm going to rewrite K prime is going to be 1/2. What do I want? I want to have, well, I have an equation for omega prime. So let's do I prime times I over I prime omega. And that inside the parenthesis is omega prime. So when I rewrite this equation, I get that my primed kinetic energy, my final kinetic energy, is going to be 1/2 I squared over I prime, right? I have I prime here, 2 I primes down there, so I get an I prime on the bottom. I get I squared on top and omega squared on top. Well, I know that I have 1/2 I omega squared times I over I prime. So I'm just taking one of the i's up top and taking that I prime up on bottom and moving it to the outside. And the reason I do this is I look and see that this thing right here is nothing more than my original K. So I get K is equal to I over I prime. And now I ask, what happened to my kinetic energy? Did it increase, decrease, or remain the same? Well, I know that I prime is larger than I. So that means I over I prime is less than 1. A small number divided by a larger number is going to be less than 1. So this value is less than 1, so K prime must decrease. So my kinetic energy, my rotational kinetic energy decreases as my arms get pulled, or as I extend my arms if I'm rotating on a stool. So it's a little bit of an abstract problem, but we were careful. We just set everything to prime, see if we could get an equation that had some original values in it. We were. So not that hard of a problem. We just had to be careful with our primes and our not primes.